Yeah, so I think last time we went over this lecture 0, Introduction to QuTiP. Right, talk about Q object, state operator. We could use the spaces. We could use the clock state. It's also coherent state. And we also talk about density matrix, thermal state, thermal density matrix, poly X, Y, Z, harmonic oscillator, creation, annihilation operator. So I mean, this we covered last time, and you can see QuTiP has a lot of useful features. The most useful one is to solve the Schrödinger equation. So this is one example. It has these Hamiltonian, and you can actually solve the time evolution, the unitary dynamics here. So this is a simple example. Sigma x, you start with 0 states and you evolve the Hamiltonian using this ME solve. And you can actually animate that. I didn't, I think I did not have this image, but you have that, I've seen that last time. You can calculate expectation value. You plot this expectation value of sigma z as function of time. And in addition to unitary dynamic, you could also solve something called a Lindblad equation with a jump operator. Jump operator corresponding to what we talked about last semester on these quantum channel. So for example, here is a Hamiltonian, A dagger A, and there's a jump operator, which is proportional to the annihilation operator. We got as the atom is this is a harmonic oscillator. So this you can imagine you annihilate a photon. So this means it's coupling to maybe the environment, exchanging the energy. Yeah, and you can solve that. So I would say a QuTiP complements nicely with Qiskit and Pennyland, and you have the tool to do the time dynamics, visualization, atoms, cavity, a lot of useful tools for quantum optics. Of course, with the influence of quantum information, QuTiP also embraces that and has an additional package. Okay, so this is notebook that I upload, so you can go to this website, the Brightspace. Yeah, it's uploaded. So we're going to look at slide that I uploaded last week. Here. So we'll go over some of these. We'll do more of a quantum info just as a beginning, and then after that we'll look at more quantum optics applications. So today we're going to look at this energy levels. Many of these notebooks are very short, so you can see just really just one page. Okay. Yeah, so on the information about this documentation. Yeah, so this basic operator we talk about, and there's a lot of info here. This is a very useful website. Okay. Yeah, so as usual, you import the visualization package from matplotlib and NumPy and QuTiP. This is about just identity sigma XYZ tensor. Okay, so this here is about energy level of 3 couple qubit. There's qubit 1, qubit 2, qubit 3. So in order to put them together into a 3 qubit system, you have to use tensor or tensor product or Kronecker product in Mathematica. And yeah, you just do the tensor. This is Z1, right? Identity I2, I3. And this X1, I2, I3. Right, and then this Z2, X2, Z3, X3. Okay. So then it says there's a list. Okay, in this list for the W1, this is coefficient. So you have these W1 lists and W2, W3, G1, 2, G1, 3. So basically Hamiltonians of this form. W1 is so the energy difference between the two level in qubit 1, W2 is the energy difference between the two levels in qubit 2 and W3 for qubit 3. And G1, 2 is interaction between qubit 1 and qubit 2 by XX interaction. G1, 3 is also XX interaction. So what it's doing here is to diagonalize that. So to diagonalize that, QuTiP has this function eigenstate, where it returns eigenenergies and eigenstate. Okay, so and then you really just are storing this energy in that, and you run through all the W1, and so this is the function to do that. So it's not stable. You said initial, these are initial values. Yeah, actually this is not used. But this will be a range of parameters here, 1.75 to 1.25, and with 50 points times this 2 pi. Okay. Just evaluate this. Compute that. What it's doing now is doing the plot. So you can see this plot. It would throw the three lowest 3 levels. So this plot, and this is subtracting the this is subtracting 0. Oh, and then divided by 2 pi using the blue, right? So this is doing that. Okay, and the plot the energy. You can maybe just show that we can bring this. For example, show this. I wonder where is the 0? Yeah. Yeah, so they plot against the lowest energy state, and actually so they plot against the lowest and then plotting the first one minus the 0, second one minus 0, third one minus 0. So this is the energy spectrum of the 3 couple qubit as a function of the W. Okay, so that's it for this very short notebook. It's just demonstrating how you do the diagonalization like how you set up the Hamiltonian and do the diagonal. So really what you learned here is this function. Okay. And the next one we have here is the flux sphere animation. This is very nice tool to have. You can visualize. Okay. So yeah, so again, you need to import the relevant packages, the block, sphere block, basis, MESOLVE, sigma. This is sigma minus, sigma x, sigma y, sigma z, and we will need to import animation. Okay. So here is define a function, cubic integrate. So with parameter w, theta, gamma 1, gamma 2, psi 0, t less. So they define these operator, x, y, z, sigma minus, and you define the Hamiltonian as we've seen previously. So you can see that this is a cosine theta times sigma z, sine theta times sigma x. Okay, so it's in the xz direction. You have these overall strength W, which is one of the input parameter. The C operator list is the jump operator list. So start with empty, assume some temperature. So at this temperature, there's an average number of photons. So this is set to be 0.5. And the rate of the jump operator applied will be related to the number of photons times the rate, there's some strength, gamma 1. So gamma 1 is a strength. If the ray is greater than 0, then you add this operator. What operator? So this is the operator which is this, it's a amplitude. So you write square root of the rate, and then you times the sigma minus. What basically here means is that if you have a two-level atoms, let me see if I can annotate. If you have two-level atoms, right? So, and if you are here, then this is actually an act of sigma minus, right, from top to down, and it emit a photon. So this is emission, and the environment may already have some photons, right? They have these n-thermal photons. So if the environment has already have photons, so this would not be a spontaneous emission. This will be stimulated in sense there's already photon there. And so therefore the rate would be proportional to this. So this why you have this. And but you could also have absorption, like absorption from the thermal state, and then you would use this process sigma plus, right? So for the atom, this is sigma minus here, and will emit a photon. Okay, and this you have to absorb photon there, and that rate is proportional to the thermal photons already there. And gamma 1 is that strength. So you take square root of that as a rate and then times the sigma minus stagger, which is sigma plus. Okay, so that's the jump operator, 2 of the jump operator. And there's also the diagonal, the SZ interaction. So basically it's a dephasing and just really just applying the square root of the rate times the sigma z, because this could also be coupling to environment. This is representing the effect of the environment. And so this is already a dissipative system. It's already non-unitary. And we can solve this. Really just saying we use NE solve and we input the Hamiltonian, the unitary part. Psi 0 is the initial state, which is the input. T list is the list of time I want to calculate the states or observable. This is the jump operator. And you have a set of, this was the code originally. I think this is the one that I uploaded, but if you run that, you will see some warning and then, okay, but let me run this. So if I see this, this will run and then, but it would give you some warning. Oh, it didn't, because I already ran it. So it would say, if you run on your end, you could try now. It would say, this will be the newer way of doing that. Maybe let me restart kernel so I can show you that. It started from fresh, so I don't know why it didn't complain. Oh, I see. Because I have not run the function. So once run the function, we'll see that. Okay. This is just showing you the sigma minus, and maybe you could also print the list of C operator. This is the jump operator, set of jump. C, did I? Oh, this you have not defined. Sorry. This is only defined inside the function, so I cannot retrieve that. Okay, let me delete this. Okay, and this is setting up W. This is qubit frequency. That's an input parameter. This W. That's the overall strength in the qubit. Theta is the angle. This gamma 1, gamma 2 are the two rates, right? It says qubit relaxation rate, qubit dephasing rate, and A equal to 1.0 is used to initialize the wave function. Okay. So this is really just saying this is 0 state superposed with 1 state and normalization. And you are looking at time from 0 to 4 with 150 points. And you simply run that function. Okay, so now it complain. It will be this will be the keyword in the later version. Okay, so if I change this, then should I use the last set of operator you want to evaluate? This is the operator you care about its value. You put it here, and you need to use E up equal to the list. Okay, if we do that, let's run again. Okay, won't complain. Okay, now we just set up a plot. Okay, this is setting up the plot the figure of the size, axis, subplot. Okay, so that's the standard way. And actually here, actually the result is not yet used. But here you set up the plot result. So we want to plot in terms of blocks of sphere because this is a qubit. So we set sphere equals none, and this is a global variable. If figure is none or x is none, then you set up that. I think you see. I want to take out because this is redundant. There's no need for that. I'm just taking out that because it's not used, right? If it's not sphere, then uh you set up this block. Okay, blocks axes, axes, and the state vector color is red. Okay, clear everything and start adding vectors. So this is expectation value that we have, right? So we have a list of C up. So 0 is sigma x. 1 is sigma y, 2 is sigma z. Okay. As different ends are the different time step. Okay, so, and then this is adding the vector. And here you also add points. Add point from 0, from time up to n plus 1. Okay, so it's plotting the trajectory. And then you make sphere. I think I'm describing in too much detail for this. This is how you set up the plot. But it's also good that we will also need have a practical tool to do this. And this is nice. You can plot animation, plot result. Okay, let's see. Oh, plot. Should I pick 0 argument? 1 was given. I think set up. I think I removed the result plot setup. But where is that? Here. The pick 0, but 1 was given. Okay, so it seems that you still need to have that. So let me just put this back. Trying to see. But this is actually not used at this point. But I think in this plot animation setup, you need to have result here. That's why, okay, that's why it was set up that way. So let's just respect that setup on this. It's going to generate like a video. Let's take some time. And then you may need to install the required package in order to have these FF MPEG or yeah, take some time. But the end is a nice simulations. So you start with up, right? Start with up. And then as time evolves, it traces our trajectory. This is cool. To help you to visualize. and seems to reach a steady state. Okay, so that's this notebook. So this you can combine. I think you can combine with QuiTiP. You could combine these plotting the animations. You could combine with QuiTiP. Any question on this? On this one? Relatively easy. Well, when you learn something new, you start with basic, but some useful tool you can combine with the other package. Okay, so the next one. So I get this from the tutorial, and there are many tutorial. You can also present for your final project. Okay, next one is more of quantum info, quantum gate. You can download. We open that quantum gate. Okay. So this one, you will need to install this package that you have now. So we talk about, I mean, installing the QuTiP like this here, basic installations. You would install QuTiP like this, but it's QIP. If you want to do something with the quantum gate, you need to install QuTiP dash QIP. And put that here. I didn't say that. Maybe later. I didn't explicitly mention that here. See if they have anyway. Quantum gate installation. But what you do is you just do the or down, install QuTiP QIP. Okay, so I'm just put comments here. So we go this. You can see you will import quantum qubit circuit there. Gate. There are a lot of gate. There's even a gate called Berkeley. C nav, C phase, C sign, Brad King. Brad King is the control swap gate. Gate sequence product, global phase, I swap, Mormer Sorensen. This is a gate specific designed initially for the trap ion. Phase gate, Q rotation, X, I, Y, and Z, S naught, screw I swap. So and totally right. So we actually we have more than what we need here. All right. So introduction. If we go, we see this is just a quantum gate. This is not a. It's nothing to do with. Okay. Okay. Control phase gate. This is the control phase gate, and you can have some phase. You could have. If you have pi, then will be this will be control Z. Put it back here. You can also write the circuit. You will say Q equal to qubit circuit. In this case, it's quantum circuit, and 2 is the number of qubit, reverse state false. So remember, there's a convention in IBM and others difference. So maybe this is how you do that. So okay, if you use false, you have this. Let me try if I use true. So the drawing does not affect. Drawing does not affect. But which tensor product, which the sequence, the order will be slightly different. So this is rotation about x. So I will just show part of this because we don't need to go through all the gates. So y, right? You can show this. Somehow when you are writing the gate, so you are using this rotation as a matrix. But when you are writing the circuit, you are using the text, the names of the gate. And you put an argument here. And which is the target. You specify which qubit. Okay, so C naught, you write the matrix in terms of this, for an object in terms of this, using C naught. But when you are writing to the circuit, you will use add gate, and this literally is name, the control, the target. Control sign, this is actually control phase gate or CZ gate that we usually talk about. So this is Berkeley gate. I don't know, maybe invented from folks at Berkeley. Swap alpha. This is swap, like, but you still have some phase. Usually the swap would be 0, 1, 1, 0, but this is, I think it's like generating the XY gate, each XY interaction. You can allow to have different phase. For example, I put pi here. What if I put 2 times pi? I put 4 times pi. This is just some phase. Pi 2. Okay. Cracking gate. Okay, so it does not show. Let's draw this. It does not. Does not draw. If you want, you can. This is how you practice, right? Let's do this and add gate. Cracking. See, it's all capital. Right. Draw 0. That's 0 targets. 1 and 2. See if it work. Yeah. Oh, so maybe writing K, you don't write as a control. Maybe just target 0, 1, 2. Okay. Hopefully, let's change this to top. Maybe here you need to control. Index out of range. Oh, maybe control is this. It's only one target. Control X. Okay, there we go. But fracking is a control swap. Maybe they just treat that as a 3 qubit gate. Did it affect how you write you write all the three qubit in the target list, and here's control. So you need to have two control. Okay, swap gate, I swap gate. Which has something here as an I in the off diagonal. And there's also square root I swap. It's the square root of this gate. Because if you multiply twice, you get back the I swap gate. Squared root of not. Okay. Hadamard. Somehow Hadamard is not called Hadamard, it's called S not. You can see how it draw the Hadamard. We just copy phase gates. Okay, and global phase, more fluorescent, qubit rotation. Yeah, so maybe this is where it should find out this and qubit rotation. QROT. I hope that will be value. Actually, there's a list. Not sure whether when you do this. Sure this will work. Let's see. List. Then it will not show the value. But this gate has two values. One thing you can do is just look up the documentation. See if you have any information. Don't have here, so maybe QuTiP. So want to look at add gate. Documentation before maybe here. Controlling the it's really not important. Okay, show values or value. argument, arg value. The use case only have one value. Yeah, so it's not tell us how to add a value. But this really the mind is just really just showing one of how you show the circuit you want to draw with much information as possible. What if I just do this? It will show this, but in fact it's not a single one. So maybe I'm just thinking if I do another one, it's not a list. It's not a list. But is it string? It's not a string. It's supported type. What is the supported? The value isn't. Yeah, so somehow we can only show one number. Okay. If somebody knows how to add the second parameter, let me know. Okay, at least from this simple search, couldn't find the use case that has two values. But as I said, it's not important. Expanding gate to larger qubit register, CNAT, you can define a CNAT with 3 qubit. So this CNAT with 3 qubit, and this is the one you can specify. Okay. I think this one is really just CNAT and for 2 qubit, but then additional qubit is not doing anything, should be identity. This is how you say which one you want to control target. Or okay, this is setting up circuit two, 2 qubit and qubit circuit, and you add gate 0, 1. So this is what we targets. Okay, this is the position followed by keyword 0, 1. This is not a control gate. Oh, yeah, I think that documentation at gate is not. Okay, maybe here you will have an arg value, any operation. Yeah, so this is what we're looking for. Maybe if any of you dig more into that, you will find the solution. Um, so this will be something useful now. You have this circuit, and you can get its unitary, like U0. So you can have the unitary as the product of all the gate. So this one is this, we see that this is a swap gate decomposed in terms of C naught. And you can do the circuit propagators, and then you say gate sequence product, you get this is a swap gate. Now there's also a nice feature that is you can decompose or in terms of C naught image. So this one, the QC0 is here for the pi swap. So you want the 2-qubit gate in terms of C naught. But do something else, like what other C, say C sign, right? You could also do the C sign. So you in terms of C sign. It's similar to IBM when we define a gate set and we can decompose. It's U2. Yeah, so they do have C sign. Okay, example of basis transformations. This is a 3-qubit circuit. You start with C naught between 0 and 1 qubit, and you add gate X rotation to qubit 0, RY rotation to qubit 1, and then RZ rotation to qubit. Sorry, the other, yeah, I should go from down to bottom to down, up. Thing is that the gate name wasn't shown properly. It should be, I mean, in previously it was showing RX and Y here, right? So it should be argue value. Let's just fix that and see if we get the plot drawn nicely. Up here and see if we right. Okay. I'm fixing this. Um, it's not really important in terms of the computation or values. So this is a U3 unitary. The transformation can either be only in the 2-qubit gate. Yeah, I mean, I don't see, I mean, the example is really just a circuit and it says basis transformation. So I don't see that connection. I mean, any unitary is a basis transformation. So this wasn't written well enough to illustrate what exactly. And this is transformation can either be only in terms of 2-qubit gate. Yeah, but we know that, but this is also 2-qubit. So yeah, I'm not sure what's the purpose of that. I view it now as an example of circuit. But this is like it resolved, like this here it's a circuit, and he said this here it says that you can resolve. It's really just decomposition. Oh, oh, yeah, this somehow when you let it resolve and then it throw these weird, it's not, does not have the gate names, only the parameter, this R quotation there. Yeah, somehow I would expect this is like using LaTeX, but it does not show up properly. Okay, but we're not here to fix it. And then if you, okay, now I understand what they mean by basis, the transformation. Transformation is really just in terms of gate, which gate they want to decompose. Okay. We already know that. Okay, so let's not, yeah, let's not spend too much time in this. The last one may be useful is resolving on non-adjacent interactions. So you can see here, there's a circuit control now from 0 to 2, and you have qubit 1 between. So let's draw this. And then, okay, this is really just, this is exactly, yeah, exactly that matrix representation. Okay. And what this QuTiP package allow you to do, you say, I want to have a adjacent gate. QC9 would be the QCA version of with adjacent gate. And it tell you what the gates you can have. So you could probably draw that. QC9 draw. So this decomposes in terms of the adjacent gates. And then you could also resolve this in terms of C0, right? So this is slot gate. So this decomposes into this and showing its value. Of course, it's not changing. The, the end goal of the circuits are the same. Okay, next is adding gate in the middle of a circuit. Okay. One can add a gate at an arbitrary position of a circuit. All one needs to do is specify the parameter index. Okay, with this we can add the same gate at multiple positions at the same time. So you have this circuit. It's useful to draw this. You see, what is wrong with this? Yeah, I don't know what's going on here. Yes. Wait, let me see the gate. Is that because of index? Just do this, see whether it would draw. Okay, let's see. That's even the simplest one. And yeah, something. Target one. I thought Python counts from zero. Yeah, weird. So that's very weird. They write target equal to one. Okay, let me just follow the example and see what they have. Okay, target. This is at one, right? So that's why it couldn't draw and see what I suspect maybe the author of this notebook wrote without plotting it, and then so does not know that actually this maybe just zero. Okay, that's not okay. We have this is the final circuit, but this allow you to you add Rx and then another Rx, but at the end you say, oh, actually I forgot, I want to add a RY, so I say index zero. What about index one? Will be in the middle. Okay, index two, of course, would be n. Let's say index three, then it would tell you probably. Oh, well, you could still add location three. Okay, so there was some mistake, right? It should be target should be one. Okay, so while we go through this, we may also find mistake of the notebook originally created. We don't need this one. Okay, user define gate. So it's like in Pendyland, in Qiskit, you can define your own gate. So let's see what they do here. They initialize a matrix. This is 4 by 4. They initialize the matrix. Yeah, so 0, 0 and 1, 1. It's 1, 0. So I can just draw it. So this is 1, 1. And then 2 to 4 is Rx. Okay, with some angle. So this will be a control Rx rotation. Okay, the second gate. Okay, yeah, it's set here. is S gate. So it's really just a 2 by 2 matrix with diagonal 1 and I. Okay, to let the qubit circuit process escape, we need to modify the attribute qubit.user gate, which is a Python dictionary. So we need to add the name of that and the function of that to the gate user gate list. When calling the add gate method, the target qubit and the argument need to be given. Okay, so here this is the 0, 1 control rotation, the other way around, and argument value. Yeah, this is SK target 1. Store this. Okay. It's propagation. Well, qubit 0 control, qubit 1. Okay, so I think this prop is really just propagator. So maybe doing this and then combine this and combine. Right, so remember you could have the evaluation, sequence, product, and propagator. Let's see. Okay. There's all depends. We just use prompts. And I guess maybe 1 is the gate 1. Yeah, 1 is going to be the gate 1. So 0 is the first gate. Yeah. And from 1 is the second gate. This is S gate. Yeah. So I thought this is like will be accumulated. No, it's just really just which gate is which according to the index. And the sequence of that is really just the multiplication. Okay, so this is very common info for the QuTiP part. This is added to the QuTiP later. Yeah, so with this gate, then you can do some exercise on teleportations. So let me open this. One on teleportations. Okay, from QuTiP import basis tensor, QIP circuit, import qubit circuit, QIP operation measurement. We haven't seen measurement yet. We only saw the gate. Okay, so yeah, you all know teleportations. So here we describe the circuit that enable teleportation. We use two classical wires, 3 qubit wires. First qubit wire represent the quantum state that will be teleported. So this define the circuit, qubit circuit, teleportation. The name is teleportation. 3, number of C bits, input state, We could draw that. So far, there's nothing here, and then you would build up. You add the circuit, the gate to build an EPR pair. So 0, 0 plus 1, 1, 1. So first, the S naught is Hadamard. S naught. Okay. For each step, you show the circuit. And just copy this. So we build up the fail state here. Okay, then Alice makes the qubit Q0 interact with EPR. So it's going to be measurement, right? So we'll measure qubit 0 and Q1 in terms of Bell basis, but the measurement will usually be in the Z basis. So we need to, in some sense, add the reverse creation of the Bell basis state. So that's what it's doing here. Then you perform measurement. And that's the short circuit. Right. So this is the reverse of this, but move to qubit 0 and 1. And then you perform measurement. Then you apply the corrections. And this in QuTiP QIP package, you could use the classical control. You want to apply X to target 2. So now we just have the measurement, but we want to do the correction. So let's do this here and draw it. Does not have. Oh yeah, it does, but it does not have. It does not have the label. It's control, right? Classical control using C0. It should draw. It should draw a. I can annotate. It would be better if this could like drawn. We could have drawn this and something like that. That would be better. Kiss has that. So. Okay. Finally, our television is ready to run. We can view the circuit. Okay, these are the instructions. The circuit can be visualized. Oh, you just say computation. You don't even need to say run. No, sorry, draw, and it draws. Okay. There's an example with plus state. Okay, there's initialized state. And initial measurement. Sorry, target 0. Initial measurement dot. Okay, measurement computational basis. Okay, so this is we can confirm our state is initialized correctly by observing the measured statistic number first. Okay, followed by which we run the circuit. Yeah, so this is the measurement. This is the probability 0 and 1. This is a plus state. Okay. Can run a circuit using qubit circuit.run, which provided initial state vector. On the circuit, including sampling, providing final results was stored in C bits result are returned as a result object. Okay, let's run this. This is the final state. This is the state vector 1, 2, 3, 4, 7, 8, with 3 qubit, right? So this is label is, yeah, 0, 0, 0. I think probably order this one. 0, 1, 0. Um, this, I think this, if we want, suppose we should, maybe this is supposed to label like this, because this will be the qubit 3. So I'm not sure the labeling of this. Oh, this, yeah, this is the final measurement. So you sometimes get 0, 0, 1, sometimes get 0, 0, 0, 1. Yeah. So the basis, we need to see how they label. This is another example with 1, and you teleport to 1. Okay. This is the final state can be here. 1 is teleported here, here, or here, or here. So maybe this give us some hint about this is supposed to be 1. These 4 location representing the qubit, 1 is 1. So 1, 1. Yeah, so we need to figure out the ordering. I don't know. I don't know what these 2 qubit values are. If the, yeah, in the usual labeling will be 1, 1, 1, and this will be this is supposed to be like this, and this is supposed to be, okay, this is 0, 0, 1. Yeah, it looks like this is as we expected. This allow us to figure out, I think the base is correct, right? So this you always get 1. Let me erase this. And how do we understand here? We're supposed to get plus state, right? It start with plus state. How do we understand this? Plus state, we should get the plus state. So we should get 0, 0. Will still be, it should be a superposition like this. It doesn't matter what the output, right? The measurement outcome, it could be 0, 1. So I should also get 0, 1 like this. 1, 0, 1, oh, sorry, 1, 0. 1, 1. This is what we supposed to get the 4 different outcome measurement. Maybe this is just showing one of them. So this is 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1. Okay, so this is really just saying there's one particular example, which is superposition. This is the measured outcome 0, 1, but it's in the superposition of the 0 and 1, which is a plus state for the third qubit. Okay, at least we figured this out. Okay, any question? Yeah, so we talk about more the QIP perspective on information processing perspective in of the QuTiP. Next time we'll actually look at more of the on the optics. I think I will upload these. There's, for example, the precession, qubit dynamics, Rabi oscillation, photon burst death. There's some for red field equation. We don't actually need to know too much detail. We just need to know there is a solver there. What need to be inputted. For example, the Hamiltonian, the jump operator, and the rate, etc. I think yeah, the rate is including the jump operator and the time, etc. Right, observable you want to evaluate. Yeah, so these I would upload these. Yeah, these each is a small, really small notebook. Really small. For example, I open this one. This is what be the first one we talk about. The precession. We already seen something like this, right? And you can make a video, right? We have seen that. Wait, was it already there? Oh, so it's actually they. Yeah, the notebook I think I uploaded. Did not have this. I just copy the one we saw earlier to here and modify. Okay, so there's one example. Photon burst and that, and you'll see some simulation there, right? It's a very short notebook. But this actually an example from simulating this Nature paper, although a long time ago, 2007. But so you can actually use QuTiP to do something at the research level. It's not just for teaching or for just animation, but it's really you can do some real research with this. Okay, so maybe this is the end of today's class, and next time will be our final class, right? And I hope you're already in the process of your final project, which is not like that long, right? You just take a notebook. Well, the length is 30 minutes. If it's okay if you talk about QuTiP, but each notebook is short, then you can maybe combine 2 or 3. But to have a story. So next time, I mean, I have, for example, 1, 2, 3, 4, 5, 6, 7 notebook. Each is short, like 1 page. Some maybe slightly longer, but I will just say as much as possible, and then we'll leave maybe 15 to 20 minutes for the evaluation for you to